title of the module Hamiltonian graphs. Today we are going to learn about Hamiltonian graphs. In 1856, Sir William Rowan Hamilton described a mathematical game on the dodecahedron as shown in the screen in a letter to his friend Graves, in which the first person sticks pins in any 5 consecutive vertices and the second is required to complete the path so that it forms a spanning cycle. This game led to the concept of Hamiltonian graphs. Now let us see the definition of a Hamiltonian path. A path which contains every vertex of a graph is called a Hamiltonian path. Now let us find when a graph is traceable. The definition of traceable is that a graph is traceable if it contains a Hamiltonian path. A concept is best understood by examples. Let us now see the following example of a traceable graph. Now let us see the definition of a Hamiltonian cycle. A cycle which contains every vertex of a graph is called a spanning cycle or a Hamiltonian cycle. Now let us find out when is a graph Hamiltonian graph. A graph having a Hamiltonian cycle is called a Hamiltonian graph. Next, let us see the definition of a theta graph. A theta graph is a block with 2 non-adjacent points of degree 3 and all other points of degree 2. We shall see some examples of Hamiltonian and non-Hamiltonian graphs now. Let us see this first example. It is actually a Herschel graph and it is an example of a traceable graph. Herschel graph is said to be traceable. Let us recall the definition. A traceable graph is one in which there is a Hamiltonian path. Now let us trace the Hamiltonian path. We will start with V10. So I start like this, I go all the way to V9, then from V9 I am going to V8 and from V8 and I am going to V7, then I am going back to V6, then from V6 I am going to V5. So now we go from V5 to V4 and from V4 we go down to V3. So from V3 then I go to V2 and from V2 I go to V1 and from V1 I go to V10. So the point of this exercise is to show that we have covered all the vertices. V10 has been covered, V9 covered, V8 is covered, V7, V6, V5, V4, V3, V2 and V1. So all the vertices have been covered in this Hamiltonian cycle and therefore this is an example of a traceable. There is a Hamiltonian path here, but if you can complete it somehow by joining it to V5, it becomes a Hamiltonian cycle, but we have stopped here and therefore it becomes a Hamiltonian path. So we have now traced the path of a Hamiltonian cycle here. We started at V10 and we have ended at V10. A traceable graph is one in which there is a Hamiltonian path. There is a Hamiltonian path in a traceable graph, but here we have created a Hamiltonian cycle. So a Hamiltonian graph is one in which you have a Hamiltonian cycle. So you can say that the Herschel graph is an example of a Hamiltonian graph as well, and we have created one big Hamiltonian cycle which is tracing all the vertices of the graph. So for any 2 vertices you can create a Hamiltonian path here. So this is the example of a Hamiltonian graph. Now let us move on to the dodecahedron. So here we can start with V5. Let us say I am starting with V5. So from V5 I go out to V4 and from V4 I go to V3. From V3 I go to V2. From V2 I go to V1 and from V1 I am going to V20. V20, after that I am going to V19. From V19 I am going to V18, then to V17 and then downwards to V16, then to V15, then V14, then V13, then I am going to V12, then I am going to V11, then V10, V9, V8, V7, V6, and finally you are stopping at the starting point itself, which is V5. Now you can very clearly see that I have traversed all across the graph and I have touched all the vertices and none of the vertices were repeated twice, and so this is a prime example of a Hamiltonian cycle. The dodecahedron graph is an example of a Hamiltonian graph. Let us see an example now for a non-Hamiltonian graph. Now we have something called a theta graph. A theta graph is one in which there are two non-adjacent vertices of degree 3 and the rest of the vertices have degree 2. So you can see in this example, vertex V4 and vertex V3 have degree 3, but the other two vertices, the other three vertices V1, V2, V6 all have degree 2. So this is an example of a theta graph. Now let us check whether it has an Hamiltonian cycle. Now if you start with V4, you can go to V1, V2, V3, V6, but still V5 will be left behind. You start anywhere else, you can create a cycle in which the rest of the one of the vertices will always be left behind, because V4, V5, V3, V2, V1, you have left behind V6. Likewise for this V4, V5, V3, V6, and you come back to V4, it is a cycle, but still you have left behind these two vertices. So it is actually a combination of two different cycles with one vertex added in between. That is the structure here, and therefore how much ever you try, you cannot create a Hamiltonian cycle here. But if you start from V5, V3, V2, V1, V4, V6, it is a sort of a Hamiltonian path, but it is not a Hamiltonian cycle. So theta is a non-Hamiltonian graph because it does not have a Hamiltonian cycle. Now let us see some theorems in Hamiltonian graphs. The first theorem is, every Hamiltonian graph is two connected. Now what is the definition of two connected? A graph G is said to be two connected if G minus x is still connected for every x belongs to G. So none of the vertices are cut vertices. So even if you remove any one vertex, the graph is still connected. That one vertex can be any vertex in the graph. That is the meaning of two connected graph. Now we are going to show that a Hamiltonian graph is two connected. So the proof for this is that let G be a Hamiltonian graph. So if it is a Hamiltonian graph, then there is going to be a Hamiltonian cycle. Let us call the Hamiltonian cycle as C, and let V be any arbitrary vertex in G. Since C is a cycle, then C minus V is connected. How is that? Because if you look at this picture and imagine that V1 to Vk is a cycle and Vi be any one vertex here. Suppose you are removing this vertex Vi, still you have another path from V1 to Vk. A cycle is somewhat like this, it is a closed path, isn't it? So from V1 to Vk it goes back to V1. So in a closed path, if you can remove one vertex, the connectivity is not yet disturbed. Therefore, the C minus V is still connected. Now the cycle C is something that is traversing over all the vertices of the graph, and therefore you can say that G minus V is also connected. So G minus V is connected for any V belonging to G. So this is basically the definition of two connectedness, and therefore there is no cut vertex, which implies that G is two connected. Therefore we have proved our statement that every Hamiltonian graph is two connected. Now let us see one more theorem now. Let S be a non-empty proper subset of vertices of a Hamiltonian graph G, then omega of G minus S is less than or equal to the cardinality of S, where omega of H denotes the number of components in any graph H. This is a theorem we are going to see here. So we know that G is Hamiltonian, S is a non-empty subset of the vertex set of G, and omega of G minus S is less than or equal to cardinality of S. So the statement is like a necessary condition for Hamiltonian graph. So if a graph is Hamiltonian, then omega of G minus S is less than or equal to cardinality of S. So that is the statement here. So to prove this, and G is Hamiltonian, which means that C is the Hamiltonian cycle of where C is the Hamiltonian cycle of G. Now you have taken a non-empty subset of the vertex set of G. So vertex set might contain some vertices. So we don't know how many vertices are there. It can be 1 or 2 or 10, we don't know. But we can assume that it is non-empty. That is the basic definition you have here. now we see here that omega of c minus s is less than or equal to cardinality of s. Why is this? Because omega of c minus s means that c is a cycle, the Hamiltonian cycle, and you are removing s number of vertices from that cycle, and this is definitely less than or equal to cardinality of s, they are saying. How is this? Is because we have already seen that a Hamiltonian graph is two connected, which means that when you are removing even one vertex, the graph still remains connected. There is only one component now, and omega represents the number of components in a graph. So, if you remove one vertex, the graph is still connected, which means the number of components is still 1. Only when you remove more than one vertex, the graph maybe becomes disconnected. That is the basic definition of a Hamiltonian graph, it is two connected. So, if you are removing s number of vertices from the graph, the number of components that you get cannot exceed the number of vertices that you remove. I hope this is clear, because omega of c minus s is definitely less than or equal to cardinality of s here. Therefore, because C is a spanning subgraph of G, omega of G minus S is less than or equal to omega of C minus S. This is also obvious, and therefore, this implies that from these two properties, from these two conditions, you can say omega of G minus S is less than or equal to cardinality of S, thereby proving our original theorem and hence the proof. The converse part of this theorem is not true, because the necessary condition is that if G is Hamiltonian, then this condition is true, omega of G minus S is less than or equal to cardinality of S. This is the theorem. Now, what will be the converse of this theorem is that if omega of G minus S is less than or equal to cardinality of S, then G should be Hamiltonian, but it is not. The best example for this is the Peterson graph. The Peterson graph, this statement will hold true, but we all know that the Peterson graph is non-Hamiltonian. Therefore, the converse is not true. The next theorem is due to Dirac, which was published in the year 1952. If G is a graph with n greater than or equal to 3 and delta greater than or equal to n by 2, then G is said to be Hamiltonian. So, we have given a condition for G to be Hamiltonian. The proof is, let us recall the concept. So, n is greater than or equal to 3, which implies that the number of vertices in the graph exceeds 3. Exceeds or is equal to 3, and delta being the minimum degree. The minimum degree is greater than or equal to n by 2. So, this is the condition they have given, and if these conditions are satisfied, we will be proving that G is Hamiltonian. Now, let us dive into the proof. The proof is, let G be any maximal non-Hamiltonian graph with n greater than or equal to 3 and delta greater than or equal to n by 2. We shall be proving this theorem by contradiction. So, reductio ad absurdum, using that technique we will be proving this. So, maximal non-Hamiltonian graph means that even if you add one more edge to that graph, the graph becomes Hamiltonian. That is the meaning of a maximal non-Hamiltonian graph. So, with these conditions and the concept that it should be non-Hamiltonian and maximal, we have created a graph G. Now, we need to, this implies that G is not complete. Why is this? Because for n greater than or equal to 3, any complete graph is Hamiltonian. And since we have n greater than or equal to 3 here, G cannot be a complete graph because it is non-Hamiltonian. So, let U and V be any non-adjacent vertices in G, and since delta is greater than or equal to n by 2, the degree of U plus degree of V should exceed greater than or equal to n by 2 plus n by 2, because delta is greater than or equal to n by 2. We can say that the normal degree should exceed the minimal degree. So, minimum degree is only delta. So, d of U plus d of V is greater than or equal to n by 2 plus n by 2, which implies that d of U plus d of V is greater than or equal to n. Let us keep this as equation number 1. Now, G is maximal implies that G plus one more edge, let us say U V. Let us keep in mind that U and V are non-adjacent in G. Alright, so U and V do not have an edge connecting them in the original graph G. I am going to create a new graph G plus U V by connecting those two vertices U and V. By connecting these two vertices, the graph immediately becomes Hamiltonian, because earlier G was a maximal non-Hamiltonian graph. So, G plus U V is Hamiltonian. Now, U V will belong to the cycle C. Why do we say that there is a cycle C? Because now that G plus UV is Hamiltonian, there is going to be a Hamiltonian cycle. And that Hamiltonian cycle we will call it as C, and this UV will definitely be inside that cycle C for all C, and that UV will definitely belong to the cycle C, where C is the Hamiltonian cycle of G plus UV. Now, G will definitely have a Hamiltonian path V1, V2, Vn. See, G is not yet Hamiltonian. So, G does not have a Hamiltonian cycle, but since we say that it is maximal non-Hamiltonian, there is a possibility now that there can be a Hamiltonian path V1, V2 so on up to Vn. Why? Because in the previous line we saw that when we added just one more edge, the graph became Hamiltonian. So, removing that edge alone, there should have been a Hamiltonian path. That is the point that we are trying to make here. So, V1, V2 so on up to Vn has a Hamiltonian path, and let us say that V1 is U and Vn is V. Obviously, U and V were non-adjacent in G, and therefore, keeping that in mind, V1 is U and Vn is V. Let us now draw them like this. So, V1, V2 so on up to Vi, Vi plus 1 and so on up to Vn minus 1 Vn. So, V1 is actually your vertex U and Vn is the vertex V. And now, let X be the set of vertices Vi such that U Vi plus 1 belongs to edge set of G, and Y be the set of all vertices Vi such that Vi V belongs to edge set of G. Now, remember, this is the Hamiltonian path that we are thinking of. So, V1 to Vn, V1 is U and Vn is V, and you are creating two different sets X and Y such that, suppose if U V2 is adjacent, U and V2 are adjacent, then you put in V1. That is the condition we are doing here. And if Vn minus 1 is adjacent to V, then Vn minus 1 enters Y. So, this is the set that we have been defining here. So, X and Y have been defined in this manner. Now, definitely Vn does not belong to both X and Y. That is the thing here. So, X union Y will not have Vn, and therefore, you have X union Y is less than n. So, in this path there are said to be n vertices, which means that the entire X union Y path will remove Vn. It does not contain Vn, and therefore, the length of the path, the cardinality of X union Y should definitely be less than n. We claim that X intersection Y is phi. So, phi is empty set, but you need to prove this, but we will be going by contradiction. Suppose there is a vertex V1 belonging to X intersection Y. So, X being the set of all vertices which are adjacent with U, Vi, U, and Y being the set of all vertices which are adjacent with V, then we are claiming that anyway there are these two sets are going to be disjoint. There is not even going to be even a single element which is common to both X and Y. Suppose not, there is one vertex, let us say V1, which is in X intersection Y, then G will have the H cycle, or G will have the Hamiltonian cycle V1, V2 so on up to Vi, Vn, Vn minus 1, Vi plus 1 and V1. So, the graph looks like this: V1, V2 so on up to Vi. From Vi I can make a jump to Vn, and from Vn, this is because we say that Vn does not belong to both X and Y. That is why we are taking a contradiction that there is a vertex. If there exists a vertex which is common to both X and Y, it will be this Vn only. So, V1, V2 so on up to Vi, then it goes to Vn, and from Vn you come in the reverse Vn minus 1 so on up to Vi plus 1, and from Vi plus 1 you can make a jump to V1. Therefore, you have now created a cycle from V1, V2 so on up to Vi. You have covered all the vertices, and then you are coming back to V1 itself. So, this is a Hamiltonian cycle. Now, this is a contradiction. It should not be a Hamiltonian cycle. Therefore, X intersection Y is empty, which implies that cardinality of X intersection Y is 0. From the earlier condition, d of u plus d of v is cardinality of X plus cardinality of Y. Why is that? Because all the vertices that are adjacent with u will come under X, and all the vertices that are adjacent with v will come under Y, and therefore, this is a cardinality of X, and cardinality of Y will be the sum of the degrees of u and v, and this is equal to cardinality of X union Y, and we know the definition of X union Y is cardinality of X plus cardinality of Y minus cardinality of X intersection Y. So, by just shifting the positions, I arrive at this cardinality of x union y plus cardinality of x intersection y, which is definitely less than n, because cardinality of x union y is less than n, that is the condition that we said earlier, and cardinality of x intersection y is 0. Therefore, cardinality of x plus cardinality of y is less than n. This is contradiction to our original equation 1, which said that d of u plus d of v is greater than or equal to n. Because of this contradiction, we started with the contradiction, and we are ending here, we are getting a contradiction here, and therefore, we can say that the graph is definitely Hamiltonian, thereby proving our theorem, that is, any graph with vertex n greater than or equal to 3 and delta greater than or equal to n by 2, then the graph is said to be Hamiltonian. Next, we shall see a simple lemma which is useful in proving the following theorems. Lemma 1, let G be a simple graph and let u and v be non-adjacent vertices in G such that the degree of u plus the degree of v be greater than or equal to n. Then G is Hamiltonian if and only if G plus uv is Hamiltonian. The proof, let G be a simple graph and let u and v be non-adjacent vertices in G such that d of u plus d of v be greater than or equal to n. If G is Hamiltonian, then obviously G plus uv is also Hamiltonian. Conversely, suppose that G plus uv is Hamiltonian, but G is not Hamiltonian. Then, as in the proof of this theorem, we obtain that the degree of u plus degree of v is less than n, which is a contradiction. Therefore, G is Hamiltonian. Next, we shall see the definition of the closure of a graph. The closure of G is a graph obtained from G by recursively joining the pairs of non-adjacent vertices whose degree sum is at least n until no such pair remains. We denote the closure of G by C of G. Now, let us see the example of closure of the graph. The closure of a graph on 6 vertices can be seen on the screen. Next, we shall see a simple lemma which is also useful in proving the following theorems. Lemma 2, C of G or the closure of G is well defined. This proof is left as an exercise. We shall now see a theorem. A simple graph is Hamiltonian if and only if its closure is Hamiltonian. The proof, let G be a simple graph, let x1, x2 so on up to xk be the sequence of edges added to G to obtain C of G. Let G1, G2 so on up to Gk be equal to C of G be the successive graphs obtained. By lemma 1, G is Hamiltonian if and only if G1 is Hamiltonian. This in turn is Hamiltonian if and only if G2 is Hamiltonian. We go so on and so forth until Gk is Hamiltonian, which implies that C of G is Hamiltonian. A corollary of the above theorem is given below. Corollary 1, let G be a simple graph with n greater than or equal to 3. If C of G is complete, then G is Hamiltonian. Proof, since the complete graphs on at least 3 vertices are Hamiltonian, C of G is complete and hence it is Hamiltonian. Hence, G is Hamiltonian by the previous theorem. Remark, since C of G is clearly complete when delta is greater than or equal to n by 2, Dirac's theorem is an immediate corollary. The next theorem that we will be studying is the Chavatal's theorem, but that theorem is open for self-study. You can refer to the script in order to study more about this Chavatal theorem. Now, we shall move on to the conclusion. Conclusion. In this module, we studied about Hamiltonian graphs, the Hamiltonian property. We checked several graphs for Hamiltonian property. We saw the necessary and sufficient conditions for Hamiltonian graphs. We studied about the Dirac's theorem, etc. So, I hope that this concept of Hamiltonian graphs was useful for your study. Try to create many more examples and learn more about the properties of Hamiltonian graphs. Kindly do the assignments and the quiz that is given at this module. Thank you.